Hello and welcome to week 5. I'm sure you are enjoying this course for last 4 weeks. Let's move ahead with more understanding. So in last week we were discussing about turbojet engine, and as we have discussed, initially we have started discussion about the turbojet engine phase 1, where we were discussing about the single spool turbojet engine. We started discussing about the two spool turbojet engine, and in last week we were discussing special case where we have introduced the afterburner in two spool turbojet engine. This afterburner can also be applicable for the single spool configuration, but in order to save the time and in order to reduce the discussion, we have focused more on two spool turbojet engine configuration with the afterburner, where we were discussing about say flight condition. We have discussed about the ground condition with and without afterburner. So that's what has given lot of clarity, I'm sure for. Now let's move ahead with the next week. This week we will be discussing about the turbofan engine. We will be starting with what are the needs for the turbofan engines, classification of turbofan engine, construction detail for turbofan engine. We will be discussing about the high bypass ratio and low bypass ratio engine. We also will discuss on forward fan unmixed single spool configuration. Again, for this kind of engine we will be discussing on the effect of various cycle parameter on performance, both in terms of say design condition as well as for the cruise condition. And let me tell you, for this course we will be having the assignments that will be online, and they also will be our multiple choice. So let's see what all we know. So this is what we were discussing about the single spool turbojet engine. For that we have discussed, we are having our initial component as intake, followed by the compressor. We have diffuser, combustion chamber, turbine, tailpipe and the nozzle. We know the importance of all these components, and we have realized these all components, they are in unison in order to complete the thermodynamic cycle, which we have discussed is named as a Joule cycle or say Brayton cycle or constant pressure cycle. Then we were discussing about the two spool configuration. We have realized the initial development of engine was with the single spool configuration. Later on, as per the requirement of the thrust, there are special requirements in terms of application for the transport purpose, where the thrust requirement was increased, and that's where it was necessary to move with the construction of the engine, where it is been configured with the two spool configuration. And if we recall, we have discussed about the fundamentals of Euler's equation, where we have realized if we will be rotating the spools at two different speeds, that's what will be reducing the overall components requirement, overall size of the engine and weight of the engine. And that's what has given the next thought process, which we name as a two spool configuration. Here this is what is representing the cut section for Pratt & Whitney two spool turbojet engine, where we are having LP compressor, HP compressor, which will be followed by the combustion chamber. We have HP turbine and LP turbine, that will be followed by say nozzle. The end was not at that stage. Later on, people, they were looking for the special requirement. It says like they want to fly the aircraft at supersonic speed, which is more than say Mach more than 0.8, and for that configuration, as we have discussed, where they have incorporated the afterburner. And we have discussed a lot in terms of what are the construction detail for the afterburner. Then we have discussed about the cycle analysis with and without afterburner in operation. So this is representing J79 GE engine, that's what is with say afterburner. So this was running equally fine, we were not having any confusion, but as we have realized, people, their expectations always they are increasing. Here till now, people, they were more focusing on what we say the term say thrust. Now let's move ahead, say what all are the benefits of using this turbojet engine. What it says, like we have our thrust to weight ratio, that's what is higher, okay, and that is the reason why it is having a special application for the supersonic aircrafts. Next, if we configure, say it is having higher speed, and this higher speed is because of higher exhaust velocity, and that is what will be giving more favor towards the application for supersonic speeds. Fuel economy and high speed, they are the major attraction for this turbojet engine. So, if we recall, we have discussed about the terminology called specific thrust. So, specific thrust for this turbojet engines, they are higher, particularly for the higher altitude where the fuel consumption is comparatively low. Then the next attraction, that is what is with the takeoff and landing performance. It says it is having better takeoff and landing, and this is because of higher thrust and faster acceleration. So, we can have short takeoff distance and we can have a steeper climb, and this is what is a requirement for the military purpose. Then later on, people they have realized this is also having benefit in terms of better specific range. That is nothing but we have introduced in our first week. It says the distance the aircraft will be traveling per the unit fuel consumption. So, all these are the favorable condition for the turbojet engine. But let us see what is happening, what is next. It says we are having benefit in terms of higher exhaust velocity, and that is what will be increasing the thrust developed by the engine. If we look at in terms of construction, no doubt it is complex, but sake of simplicity we can say it is simple in design, okay, compared to what most engines or most recent engines we are having. And it says it is working efficiently for the supersonic speed. But now the scenario has come, what will happen if I am flying my aircraft at subsonic speed? Now people they will start thinking of improvement of the efficiency. If you realize, we have discussed about the three efficiencies: thermal efficiency, propulsive efficiency, overall efficiency. So, over the year people they have realized now we should think in terms of improvement of the efficiency, and that too when we are flying at the low speed, because these engines are working absolutely fine for the supersonic speed. Then the specific fuel consumption, that means this is what is related with our fuel economy. Then the next component, it says the noise level during takeoff and landing, that seems to be higher for this turbojet engine. So, now the question is, how do we address these questions? How do we address the subsonic speed flights? How do we address with, say, improvement in efficiency, reduction in specific fuel consumption, reduction in noise level? So, can you think in sense like what can be done? So, let us try to understand what we have in our fundamental understanding. It says my net thrust for the engine, it is given by momentum thrust minus momentum drag and pressure thrust. So, we can say it is nothing but my gross thrust minus my momentum drag. So, you are aware of all these terminologies. So, let me put this engine. Suppose if I consider I am writing my thrust, this thrust suppose I am considering as a momentum thrust only for the simplicity. Now, here in this case, suppose if I consider I want to increase my thrust. So, there are two ways to increase this thrust. One, it is either to increase the exhaust velocity, or second, that is what is to increase the mass flow rate. Now, the thing is, what we understand about the exhaust velocity, we have tried exploring using our turbojet engine. What we realize, if we increase our turbine entry temperature, that is what will lead to give higher enthalpy at the entry of our nozzle, and that is what will lead to increase the exhaust velocity. Now, by providing this turbine entry temperature to be higher, what is happening? We have our difficulty in terms of blade material. So, that is where the turbine entry temperature, that is what is coming as a constraint for us. Next is in terms of improving the overall pressure ratio. So, in last week we were discussing about the two spool configuration. There we have realized increasing the overall efficiency in combination of turbine entry temperature that plays important role. Not only changing the overall pressure ratio will make the sense. So, suppose if we consider higher turbine entry temperature in combination with higher overall pressure ratio, that is what will lead to increase my exhaust velocity. If that is the case, under that configuration we have moved with say 2 spool configuration, and it says by doing so basically we are increasing our number of components for the engine, and that is what will lead to increase the overall size of the engine and also the weight of the engine. This weight of the engine, that is what will be reflecting in terms of drag, and it is having impact on specific fuel consumption. One more possibility what we have is my nozzle area. We can say if we are able to increase the nozzle area, by that way also we can increase the exhaust velocity. So, by manipulating with the nozzle area we can able to have this exhaust velocity to be managed, and that is what we have realized for say engine with afterburner, that is what is having variable area nozzle, that is what is taking care of the variation of the thrust. So, this is what all we know up till now. Now, the next possibility what we have is mass flow rate. Now, the question is what we mean by mass flow rate and how do we increase this mass flow rate. Suppose if I consider this is my engine, and if I want to increase my mass flow rate, so you can understand for that configuration we need to increase the size of the engine, okay, and with that we will be having our exhaust velocity, that is what will not be giving the benefit in terms of increase of thrust. So, what can be done? Say suppose I say let us try in terms of low mass flow rate with higher exhaust velocity, higher mass flow rate with low speed or low exhaust speed. Let us see what is the meaning of that. So, here in this case this is what we know. Let me put this as m dot into V exhaust, and this is what we say in terms of my mass flow rate. So, let me put this kind of construction. So, if you look at carefully you can say here this is what is my turbojet engine only, and in front we have connected with some additional rotating device. This rotating device I say as a fan. Suppose if I consider I am putting say larger size fan, then it will be sucking the air from the atmosphere here, and on upper side of our main engine or turbojet engine, or rather I say now as a core engine, I am having the duct. So, this is what is a duct on the outer side. Okay. So, let us try to look at what exactly and how exactly this machine is working. So, in this case we know this is what will be giving me my exhaust, and that exhaust I say as a primary stream, where my thrust that we can represent as m dot into V. So, we can say here we will be having say exhaust velocity which will be coming out from the core engine. Same way on upper side, since we have provided this with the duct, I say that as a secondary stream. So, here in this case what will happen, this fan it will be compressing the air, and that air that will be passing through this duct, I say it is bypassing through this duct, okay. And at the end we are having the nozzle, additional nozzle which is provided. I say there also we will be having our exhaust, that is m dot into V. So, in this configuration we are having two thrust values coming. One, it is because of primary stream, and second, that is what is because of my secondary stream. So, I will say that as a hot thrust which is coming from the core engine, and what is coming from our secondary stream I say that as a cold thrust. So, here in this case if we look at, we have this bypass duct, that is what is of smaller diameter, smaller dimension, That is the reason why I am naming that as a low bypass ratio engine, and that is what is taking care of low mass flow rate and higher velocity. Okay. Now, you will say, sir, why do not we think in a other way? In this equation, now it is giving us some other kind of indication. Suppose if I will be increasing my mass flow rate to high value and my velocity, exhaust velocity to be lower value. Suppose let me put this kind of configuration here. What is the case? Here this is my core engine, or it is similar to what we have in terms of turbojet engine, and on the front side we are putting large diameter fan. Okay. We can compare here, this diameter is a smaller diameter fan, here this is what is large diameter fan. Now, here in this case I will be having this primary stream, that is what we say, it is generating my hot thrust, it is m dot into V exhaust. Here from the secondary stream I will be having m dot into V exhaust, that is what we say cold thrust. So, we can say we are able to manage our flow in terms of higher mass flow rate and lower velocity. Now, the question will arise, what is this? So, this configuration, that is what is called turbofan configuration. Okay. So, what was the limitation here for the turbojet engine? Let us discuss about that. So, major concern, that is what is, in order to handle large mass flow rate, you need to have larger dimension, that is what we are providing here also. But the thing is, by having that large mass flow rate, we are not able to achieve higher thrust, because my exhaust velocity will not be reached to what number we are looking for. Okay. So, here this is we say as low bypass ratio engine, and this is what we say as high bypass ratio engine. It says around approximately 70% of the thrust that will be generated by the fan nozzle in high bypass ratio engine. Similarly, for the low bypass ratio engine, it says it is having major contribution compared to our cold thrust. Okay. Now, let us see, like this has given one new thought process, and that is what has given idea for making new kind of engine variant. What all are the benefits of using these engines? So, let us see, very first we have discussed that is what is in terms of increasing the thrust. Let us try to look at second case. Here in this case, this is what is our HP turbine. This HP turbine, we know if we are able to increase the turbine entry temperature, we can increase our thrust, we can improve our thermal efficiency, we can improve our overall efficiency. What was the constraint? We cannot move beyond certain value because of metallurgical constraint. Now, here in this case, since my bypass air, that is what is passing through this casing, that is what will be giving the cooling action. Okay. Now, let us look at this high bypass ratio engine. Here also, suppose if I consider this is my HP turbine, which is operating at high temperature, and that is what will be surrounded by the cold air, and that is what will lead to give the cooling effect, and that is permitting our turbine entry temperature to be higher. Okay. That is what is very good or first benefit. Now, let us look at what is happening next case. So, here as I told, we are increasing our turbine entry temperature. So, what we were looking for in terms of limitations with turbojet engine, we are trying to rectify. Here this hot gas, that is what will be exhausted from this nozzle. When it is coming in contact with the atmosphere, say suppose if I say turbojet engine, because of searing action we will be having lot of noise that will be generated. Now, here in this case what is happening, say what exhaust gas coming out from the hot gas, that will be surrounded by the cold air, and that is what is helping in suppressing the noise. Similar here in this case we are having high bypass ratio engine, that is what will be suppressing the interaction between hot gas and the atmospheric air, and that is what will lead to reduce the noise. That is what is a need for the future engines. Okay. So, this is what is our second benefit. So, if we consider say our application of these engines for say military purpose, where over the year the technology got matured and people they come up with say radar system. What this radar used to do, it will take the IR signature. IR signature means the hot section or hot spot of the engine. Suppose if I consider say projectile, maybe missile or maybe aircraft, that is what is flying at particular speed, at particular altitude, and if we are having the hot spot. So, hot spot we will be having one hot spot we will be having at this turbine, second that is what will be at the exhaust and at the entry. So, because of this hot spot that can easily be identified when it is flying at particular altitude, and it may be possible that you can just sort that. Okay. Now, here in this case, since we are having this outer layer, that is what will be reducing the temperature, this will be reducing the IR signature. So, that is also one of the benefit, we can say that as a stealth technology. So, for that application this is what is of great need. So, such kind of engine what we say as low bypass ratio engine, that is the benefit. Similarly, say for high bypass ratio engine, that is also IR signature is equally important. It is not that people they are shot down only military aircrafts. There were incidents in the world where commercial aircraft also were targeted. So, now the situation is by providing this bypass ratio configuration, we are able to avoid that kind of IR signature. Okay. So, now let us see like what are the use of this engine. Say low bypass ratio engine, if we are looking at, since their dimensions are smaller, slightly higher compared to turbojet engine, which can easily be fitted in military aircrafts, because we are having constraint with the space available to accommodate the engine, and that is the reason why this low bypass ratio engine that has major attraction towards say military engines or military aircrafts. Even for say business jet, people they are looking for special kind of application where we have low bypass ratio engines. Most recent commercial aircraft where the specific fuel consumption, fuel economy is of great importance, where these high bypass ratio engines are used. So, if we look at globally, almost 90% of our aircrafts they are flying with high bypass ratio engines. So, now from this week we will discuss about this turbojet engines dedicatedly. Okay. Now, let us move towards the next. So, let us try to understand here in this case in construction detail, as we have discussed, we have initial component, that is what is fan. From here my air, that is what will be bifurcated in two ways. One I say air which is entering inside my core engine, I say this as m dot core. Same way other air that is bypass or bypass through this duct, I say that as a m dot fan. Now, this air that is what will be getting compressed in compressor, it may be with the single spool, two spool or three spool configuration. We will be discussing as we move ahead with. Next component what we have is our combustion chamber. The working principle for combustion chamber for this turbofan engine, it is same as say turbojet engine. We are having turbine section, that is also working similar to what all we have discussed in terms of turbojet engine. We are having say tailpipe and the nozzle. Now, here in this case the construction it is different, same way the cycle also will be different. The additional parameter which will be coming here, let me introduce the parameter that is called bypass ratio. This bypass ratio, it is nothing but bypass airflow divided by primary airflow. Primary airflow is nothing but I say it is m dot cold divided by m dot hot. What we mean by m dot cold? It is say my fan airflow rate divided by m dot core. So, different books, different literature available in open source, they are using different terminology, but we need to realize here we are having a parameter called bypass ratio, and that bypass ratio is a function of my mass flow rate passing through the fan divided by mass flow rate passing through my core engine. Now, do not get confused here. The question will come, what is entering inside the fan? So, here in this case I say my m dot fan is nothing but beta into m dot core. So, basically at the entry what free stream airflow I have, that we can write down, it is nothing but m dot core plus beta into m dot core, it is 1 plus beta into m dot core. So, be careful, this is what we say engine flow rate, and here this is what I say as fan mass flow rate, and this is my say core mass flow rate. Okay. Now, since we have introduced this parameter, it is called bypass ratio. So, over the year people they have defined this bypass ratio with different terminology. Say initially during 70s, say the bypass ratio was in the order of 2:1, which people now they are saying as a low bypass ratio turbofan engine. For commercial application during 80s, it was having bypass ratio in the range of 4:1. Later on it reached to 8:1 in 90s, and during 2010 it reached to 12:1. The bypass ratio increase we will be discussing as we move ahead with. These days people they started talking about ultra high bypass ratio engine, where bypass ratio is more than 12. Okay. So, now this is what we say is a future. So, now let us try to look at this what we know as turbojet engine, this what we know as a low bypass ratio turbofan engine, and we have high bypass ratio turbofan engine. Now, the question may arise in the mind, who has given this thought, from where this idea has come. So, let us look at here what it says. During 1936 to 46, there were two companies, Powerjet and Metropolitan Vickers. Now, they have merged with some other companies, but they were the pioneers who has given the concept of ducted fan turbojet engine, what we are naming as a turbofan engine. But that time nobody has shown the interest, and they were considering this as most complicated turbojet engines, and that is the reason why it was not having too much of attraction during those days. Later on, say 10 years later, Rolls-Royce they have introduced such bypass ratio turbojet engine with bypass ratio in the order of 3 or more. Later on in 65, GE has come up with TF39, which was having bypass ratio of 8, and still they are having say GE90, which is having bypass ratio approximately 9, LEAP engine, that is what is having say bypass ratio in the order of 11, Gen X, that is what is having say bypass ratio approximately 12. So, we can say this is what is representing how this turbofan engine that has come into the existence. Okay. So, now I am sure you have understanding, you have got the idea what we mean by turbojet engine and what we mean by turbofan engine. So, this is representing what we have defined in terms of low bypass ratio, moderate bypass ratio, high bypass ratio and ultra high bypass ratio fan configurations. So, here if you look at say for low bypass ratio engine, they are having bypass ratio in the range of 0.25, 0.3, 0.57, and ultra high bypass ratio engines which are having say bypass ratio in the order of 12.5:1, 14:1, and our thrust requirement, that is what is increasing. And if we look at clearly say for this low bypass ratio engine, they are having say afterburner also in operation, which we say dry engine thrust or say wet engine thrust. Okay. Now, let us try to look at how we have come up with this kind of idea. What we know, my jet velocity coming out from turbojet engine is very high. Okay. This is a result in say poor propulsive efficiency at subsonic speed, as we have discussed, that has a limitation. Now, this propulsive efficiency what we are defining, we know if we are having our exhaust velocity to be higher, propulsive efficiency will go down. For that case, say this we are looking for our commercial aircraft as well as for military aircraft, because we are planning to have our flight subsonic condition. Okay. Now, the question will come, how do we improve this propulsive efficiency? Okay. So, the question is, can we do something based on what all we know? Let us see what is your thought process, how you are understanding this case. What we want to do, what is our target? I say our target is exhaust velocity. How do we reduce this exhaust velocity? So, let us make a thought process. We know our engine very well. The case is the hot gas which is coming out from the LP turbine, and that is what is passing through the nozzle. So, in between, if we will try to put some device which will be useful in order to reduce the energy, that is what is entering inside the nozzle. So, we can say if we are reducing the enthalpy entering at the nozzle, we can say by doing so we are able to reduce the jet velocity coming out from the nozzle, and that is how we can say we are able to improve the propulsive efficiency. Okay. Same way, what all energy we have extracted can be used somewhere else, so that also will lead to say increase of thrust, or that will lead to give the exhaust velocity, and by doing so we will be able to increase the propulsive efficiency. So, it is little tricky. Let us see what is the thought process. It says when we are having say LP turbine, for this LP turbine we will be putting the additional stage in LP turbine. So, it will be extracting the energy from that LP turbine. So, at the exit of LP turbine my enthalpy will be lower, and that enthalpy that will be entering inside the nozzle, and that is what will lead to give the exhaust velocity to be lower. Now, the same LP turbine which we are used for this extraction of energy can be used to rotate the compressor at low flow rate and high pressure ratio, or maybe high flow rate with low pressure ratio. So, let us look at what is the meaning of that. We can increase one compressor stage, or maybe we can incorporate the fan which will be rotating at low speed, that will be extracting more amount of air and will be operate at low pressure ratio. So, by doing so what we are doing is we will be getting lot of energy from the primary stream, as we have discussed, because we are having low velocity there. Same way the secondary jet what we have, it is getting reduced, and that is what will be lead to improve the propulsive efficiency as compared to our turbojet engine. And this is what is a thought process for the development of turbofan engine compared to your turbojet engine. So, we must realize what are the requirement, technological requirement for incorporating the fan, and how do we rotate that fan, and by doing that what basically we are doing. So, now we can say we are moving towards the improvement of efficiency, and that efficiency we say as a propulsive efficiency. Okay. Now, the question may come here in this case, it says like if not turbojet engine, let us move with the turboprop engine, but the limitations with the turboprop engine is say mainly there are many limitations with the propellers. Suppose if I consider propeller to be rotated at the high speed, it has its own constraint with the material, it has aeroelasticity issue, it has vibration issue. So, it says if we are using fan, that will not be as larger as the propeller, and that is the reason why we are able to rotate that at high speed and we can achieve the transonic speed for the aircraft, which was not possible with the turboprop engine. We know turboprop engine can fly maximum up to Mach 0.4, 0.5. Beyond that, it has a limitation. Same way, if we look at the fan, that is what is stable. It is not having major issue with the vibration, and that is the reason why it is not say creating any disruption of the airflow. Next, if we look at, suppose this is representing say turboprop engine and this is representing turbofan engine. We can say all our rotor blades or fan blades which are inside this casing, we can say it is placed inside the duct, and that is what is giving the aerodynamic benefits, and this is what will increase in terms of efficiency. For this case, we are having limitations in terms of tip leakage losses. So, we can say over turboprop engine there is an attraction towards say turbofan engine. Okay. Same way for gear turbofan engine, we will be discussing this in detail. We are having one dedicated week for gear turbofan engine. In that case, since this gearbox which has been used to rotate the fan, which is rotating at the low speed and it is having smaller dimension, so it will not give the penalty in terms of weight as well as drag. That is what is a problem with our turboprop engine. Okay. The smaller fan is more efficient and take the air at the greater rate than that of my propeller configuration, and that is what will lead to improve the thrust. The turbofan engine is much more efficient design compared to turbojet, and it is giving more benefit in terms of high performance velocities, and that is what has attracted the attention towards say turbofan engine. So, these turbofan engines, they are having so many benefits compared to our turbojet and turboprop engines. Now, the question will come, we have introduced the parameter, one parameter it is called bypass ratio, second I say fan, and we have discussed the pressure ratio of the fan. So, the question obviously will come, what will be the best value for the bypass ratio and what will be the best selection for the pressure ratio. So, here this is representing the bypass ratio, propulsive efficiency and fan pressure ratio. So, if we look at here, it says with increase of bypass ratio, we have improvement in propulsive efficiency. It will be improving up to some limit, and then after this increase of propulsive efficiency is not at a great rate. Same way here, with increase of bypass ratio, the fan pressure ratio, that is what is going to reduce. So, here if we look at carefully, this is what is representing where we are having high to medium pressure ratio of the fan, and we are having say bypass ratio that is in the range of 20-25. It is giving great improvement in propulsive efficiency, and this is the range where we are having low fan pressure ratio, but the influence of bypass ratio on say propulsive efficiency is not that high. So, we can say now it is giving us idea what need to be the selection criteria for the bypass ratio, what need to be the selection criteria for the fan pressure ratio, because this all are related with the component efficiencies. If we are moving with say larger size diameter of the fan or maybe with the large size casing, that is what will lead to increase the weight of the engine and weight of this component also. So, based on what is our application, we need to decide with the bypass ratio as well as the fan pressure ratio. And we should not forget our major concern is jet noise suppression, and second, that is what is with the less susceptibility to infrared detection. Now, this is representing the global trend for the variation of bypass ratio. As we have discussed, it has started with the Rolls-Royce, and later on if we look at over the years the bypass ratio that has reached in the range of 12, say for GE engine, for Pratt & Whitney 1000 CFM engine, we are having the current bypass ratio is in the range of 12:1. Now, here this is representing the cruise fuel consumption. So, as we have discussed, the thrust only was not the target. People they have realized, people they find their suitability in terms of fuel economy also. So, they have taken turbojet engine as a reference engine, and with that they have shown over the year the variation of bypass ratio and the improvement in terms of fuel consumption. So, low bypass ratio engine, medium bypass ratio engine, high bypass ratio engine, this all that represents say very high bypass ratio or ultra high bypass ratio engines. Okay. Similarly, this is what is representing the specific fuel consumption reduction compared to single spool configuration, two spool configuration, twin spool configuration with fan, advanced propeller technology, propeller fans. So, over the year our target is more towards the improvement in terms of fuel economy, okay, and that is what has led to have lot of research and development activities which are going on. So, currently all these companies they are ready with the engines for say 2025, 2030. They people they are doing their research for the future engines that will be coming maybe in 2035 or 2040, and that is what is running whole business for gas turbine engines applicable to aircraft. Okay. Now, here this is representing the trend for aero engine efficiency. As we have discussed, we have introduced three efficiency. One, that is what is say core efficiency or the thermal efficiency. Secondly, we have discussed that is in terms of propulsive efficiency, and the product of thermal efficiency and propulsive efficiency that we have defined as say overall efficiency. So, over the year our interest is to improve the thermal efficiency, our interest is to improve the propulsive efficiency. So, we can say here this is representing turbojet engine compared to that low bypass ratio engine that has shown the improvement in propulsive efficiency and core efficiency, and in sense overall efficiency also. Now, we are moving towards this direction where it says like we want to have improvement in propulsive efficiency, thermal efficiency, overall efficiency, and here these lines which are representing the specific fuel consumption. So, we are more moving towards the fuel economy, and that is where we have unducted fan engine, we have advanced unducted fan engine. As we move ahead, we will be discussing about the future engines also in this course. That is what will give more understanding, more joy to you all. Okay. So, this is the era where we have this course it is been designed for. So, whole discussion now onwards will be in this regime where we will be discussing about the improvement of propulsive efficiency, improvement of thermal efficiency, improvement of overall efficiency, and improvement of specific fuel consumption. So, now in overall let us try to realize this turbofan engine. If you recall, we have discussed in earlier class also, it has been classified mainly in terms of forward fan and aft fan configuration. Forward fan, we say my fan will be placed in the front, that is what we say as a forward fan configuration. When we will be having fan, it is been placed in the rear side, that is what we are defining as a aft fan configuration. For the forward fan, it says mixed flow configuration, unmixed flow configuration. What is that? That all we will be discussing in coming weeks. We have non-afterburner, with afterburner. So, you can realize these turbofan engines also have configuration where we can incorporate afterburner, and we know these afterburners mainly being used for the military purpose. Okay. This forward fan configuration further we can say as a single spool configuration, maybe 2 spool configuration, 3 spool configuration. We will be discussing what all we mean by single spool, 2 spool and 3 spool. We have current coming up engine, that is what is in operation, say gear turbofan engine, ungeared turbofan engine. We also will be discussing about the high bypass ratio, low bypass ratio, and as we have discussed this low bypass ratio engine, that is what is mainly being used for military purpose, where we will be discussing about non afterburning and afterburning operation. So, you can understand now onwards what all we are discussing or what all we will be discussing in week 5, 6, 7, 8 and 9. That is what is dedicated to turbofan engine, and that is what is recent engine, future engine and future upcoming engines we will be discussing about. So, with this here I am stopping with. I am sure you have now more clarity compared to what all you know till now with turbojet engine and what we mean by turbofan engine and how this turbofan engine that has come into the picture. So, it is just to explain you what and how you need to understand these turbofan engines. So, thank you very much. We will be discussing in the next lecture how do we do our cycle analysis and performance parameter calculation for such turbofan engines. Thank you.